Hey, welcome back! In part 1, we looked at how GitLab Runners work, deployed one to Kubernetes, and wrapped up with overprovisioning to keep things responsive. If you haven't seen that yet, you'll find the link below or up here somewhere. I'd recommend watching it first if you want to follow along with all the steps we've taken so far. Otherwise, let's pick up right where we left off and dive into the configuring storage. Sometimes a node hosting executor pods can run low on local ephemeral storage, a condition known as disk pressure. When this happens, the pod might either get evicted or fail to start altogether. This usually occurs when too many storage-heavy pods are scheduled on the same node. The executors can run into this issue since they use local ephemeral storage by default, specifically an empty dir volume, which can quickly fill up with things like repositories, build packages, and other temporary files. To prevent this, you can configure executor pods to use ephemeral persistent volume claims, which provide dedicated storage that exists only for the pod's lifecycle. However, this will only work if dynamic volume provisioning is enabled on your Kubernetes cluster. Now let's take a look at the configuration. Once again, we'll focus only on runner's config since everything else stays the same. There is no simple built-in way to configure PVCs for our executor, so we'll need to patch the pod spec directly. But before we can do that, we first have to enable the feature flag for advanced pod configuration. Enabling a feature flag is straightforward. We just add it to the runner's environment section like this. Once that's done, we can define runner's Kubernetes pod spec and patch our executor pods. Here we're creating a new ephemeral persistent volume, which will use the default storage class and provision 1 GB volume for us. This volume is then mounted inside both the build and helper containers at the path where the executor pod expects its local storage to be. Alright, let's update the runner. And there it is. The new runner is up and running, ready to take on new jobs. Now let's trigger the pipeline again. And here we go. You can see the new persistent volume being created. Once the job is finished, the volume is automatically cleaned up as well. So let's recap. To avoid disk pressure and pod eviction, we configured executor pods to use ephemeral persistent volume claims, PVCs, instead of the default empty dir volume. Since there is no built-in way to do this, we patched the pod spec, enabled the advanced pod configuration feature flag, and defined a 1 GB ephemeral volume mounted inside the build and helper containers. After updating the runner and triggering the pipeline, we saw the persistent volume being created dynamically and cleaned up automatically once the job finished, ensuring efficient temporary storage for executor pods. Alright, that wraps up our work with ephemeral storage and PVCs. Now let's move on to the next topic. To further speed up our pipelines, we can take advantage of caching. Caching is typically used to store build dependencies, tool caches, and other frequently accessed files. We can enable caching in the GitLab pipeline, and by default, the executor stores a cache locally, which means it gets wiped out every time a new job runs. To make caching actually useful, we need to enable distributed caching and use S3 storage to persist cache contents across job executions. For demonstration purposes, I'll deploy a simple MinIO instance in my cluster since it provides an S3-compatible interface. Here is the configuration for the Helm chart. I'll deploy MinIO in standalone mode with a single replica. Since I want MinIO to run on system pool node, I've set a node selector and added a toleration to make sure it's scheduled correctly. MinIO also runs a job after installation to create the initial users and buckets. I want this job to run on the system pool node as well, so I've configured that here too. Next, I'm setting the admin user and password directly in the values file. However, this is not recommended for the production environments. Instead, you should either create a Kubernetes secret before deploying MinIO, or use Helm's set parameters to provide credentials securely. In my case, since this is just a temporary instance, I'm keeping it simple and defining the credentials directly. Finally, I also create a user and service account for our runner, along with the bucket where the cache will be stored. Alright, let's deploy MinIO. First, we'll add the Helm repository for the MinIO chart. Now we'll deploy MinIO using the values we configured earlier. And there it is. MinIO is up and running. Now we are ready to use it for our GitLab cache. Now let's take a look at the configuration. Here we specify the secret where the credentials for the cache system are located. And for all further settings, we'll focus only on runner's config since everything else remains the same. We've added two new sections to our runner configuration: runner's cache and runner's cache S3. The runner's cache section defines a type of cache. In our case, we are using S3. But you could also use Google Cloud Storage or an Azure Storage account. The path specifies where the cache is stored in the selected backend, and shared enables cache sharing between multiple runners. The runner's cache S3 section configures the S3 specific settings, including the server address, bucket name, and location. Since our executor runs inside the cluster, we can use a cluster internal URL to access MinIO. The bucket name matches the one we created earlier with the Helm release. For MinIO, the bucket location is not relevant, but the protocol requires a value, so you can set this to anything. And because our MinIO instance doesn't use HTTPS, we need to set insecure to true to tell the S3 client how to access the bucket. And that's basically it. Alright, let's deploy the changes. We first need to create the secret with the credentials for our cache with the same name as used in the configuration. And now we can update our runner. And there they are. Everything is updated and ready to go. Now the next step is to update our pipeline configuration to actually use the cache. Here's the updated configuration. Let's go through the changes. I won't dive too deep into the pipeline details here, but if you'd like a dedicated video on this topic, just drop me a comment and I'll make one. So I've added 3 different caches. One for the Yarn module cache, one for Node modules, and another one for Vite build cache. To speed up the pipeline, it's also important to set the right cache policy. The push-pull policy is a default and should be used if the cache needs to be updated during job execution. This ensures the cache is uploaded back to the storage after the job finishes. The pull policy, on the other hand, works like an immutable cache. Use this when you know the cache files won't change or when changes aren't relevant to the cache. To make caching even faster, I've enabled the FastZip feature flag and set the cache and artifact compression level to fast. You could also use fastest, but this would increase the compressed size, making uploads and downloads take longer. I recommend experimenting with these values to see what works best for your setup. And finally, I've updated the job definitions to use the caches we just defined. I also removed yarn install from the build job, since I'll now be relying on Node modules from the cache. Here is a look at our cache bucket. As you can see, it's empty right now. Alrighty, let's trigger the pipeline. The lint job is done, and now we can see that the cache has new entries. The build job is finished as well, and everything worked as expected. Node modules were available for the build. Now in this small example, we don't really see the huge impact of caching. But trust me, on a larger project, when set up correctly, caching can massively speed up your builds. So to sum it up, to speed up our pipelines, we set up distributed caching using S3 storage instead of local cache, which gets wiped out between jobs. We deployed a MinIO instance, configured it for our runners, and created a cache bucket. Then, we updated our runner configuration to enable S3 caching and adjusted pipeline settings to use separate caches for Yarn modules, Node modules, and Vite builds. We also optimized cache policies and enabled FastZip compression for better performance. After running the pipeline, we saw the cache being populated and reused, proving that caching can significantly speed up builds in larger projects. At this point, we have a fully functional runner with some custom tweaks, and we can run pipelines where all jobs use this runner. But there is more. We can actually run multiple different runners inside our Kubernetes cluster, each serving different purpose. For example, we can create runners with different resource requirements, such as those optimized for jobs with high CPU or memory usage. We can deploy architecture-specific runners targeting platforms like ARM or AMD. We can even configure runners on specialized node pools, such as nodes with GPU acceleration for AI or ML workloads. So let's put this to the test. We'll create 2 additional runners. One will be similar to our existing runner, but with more CPU and memory, and the other will be configured to target ARM nodes. Now we are going to register 2 additional GitLab runners, just like we did for our first deployed runner. The first runner will be tagged AMD64 large, and I also create Kubernetes secret for its token so we can reference it later in our configuration. The second runner will be tagged ARM64 large, since it will have the same resource allocations as the AMD64 large runner. Just like before, I'll create a Kubernetes secret for its token as well. Alright, now let's take a look at the configuration. Here's the configuration for our more powerful AMD64 large runner. The only differences from our previously deployed runner are the increased resource allocations and the GitLab authorization secret it uses. The ARM runner configuration is almost identical to the AMD64 large runner, with just a few key differences. Once again, we reference a different GitLab token secret, but this time we also need to adjust the node selector and add a toleration. Since ARM nodes have a CPU equals ARM taint, we need to specify a toleration, so that our runner pods can be scheduled on the ARM node pool. Alright, let's deploy the new runners. And there we go. All 3 runners are up and running, ready to take on jobs. To test our new runners, I'll build a Docker image for a simple Hello World Express application. But instead of just building for one platform, I'll create an image for both AMD and ARM architectures using our newly deployed runners. Now let's take a look at the pipeline definition. I've added 2 new jobs to our pipeline. The first job builds the image using Kaniko, and I'm leveraging parallel builds to create images for both AMD and ARM architectures. The second job creates a multi-architecture manifest for the build images and pushes it to the GitLab image repository under a common tag. This job only starts after both build jobs for AMD and ARM have successfully completed. These new jobs will be triggered when I manually run the pipeline and set the build variable to image. Alright, let's try it out. I'll trigger the image build pipeline. Now we can see that the AMD build job started almost instantly, while the ARM job is waiting. Since no ARM node is currently active, Kubernetes needs to scale one up first. And there it is, the ARM job has finally started. Now the manifest job is running, combining both images into a multi-architecture manifest. And that's it! The pipeline has successfully finished. And there we have it, a multi-architecture Docker image built entirely by our self-hosted GitLab runners on Kubernetes. Let's quickly recap everything we've accomplished in this tutorial. We started by setting up self-hosted GitLab runners on Kubernetes, learning how runners poll for jobs and execute tasks inside isolated environments. Next, we deployed our first runner and explored how to optimize performance, including configuring resource limits, node selectors, and tolerations. To further improve scalability, we introduced an overprovisioning pod with priority classes, ensuring that a node is always ready to handle new jobs while keeping resource usage efficient. We also tackled storage limitation, configuring ephemeral persistent volume claims to avoid disk pressure and ensure that executors have the storage they need. To speed up the pipeline execution, we implemented distributed caching using MinIO as an S3-compatible storage backend. We then integrated caching into our runner and pipeline configurations, significantly improving build efficiency. We extended our setup by deploying multiple runners. one optimized for high resource workloads and another targeting ARM nodes, allowing us to build for multiple architectures. Finally, we put everything to the test by building a multi-architecture Docker image, leveraging Kaniko and parallel execution, and successfully pushing our images to GitLab image repository. With this setup, we now have a scalable, flexible, and efficient CI/CD system running entirely on self-hosted GitLab runners in Kubernetes. That wraps up our journey of setting up self-hosted GitLab runners on Kubernetes. If you found this helpful, let me know what you think in the comments. Thanks for hanging out with me and see you in the next one.